It's time for a brand new chapter, AB students. It's chapter 3.
Now we're off Schoology, every single grade, and that's the story of the evolution of Wade.
So today we start off with lesson 3-1, obviously. And first we have a review problem from your old math classes. If you have a circle, can you draw what's called a tangent line? There's a whole section back in the integrated classes of tangent lines, secant lines, chords, the diameter, the radius. So, pick any point, doesn't matter. I'll just pick a random point. And a tangent line, each point on a circle has only one possible tangent line. It is the line that nicks the edge of the curve, but does not go through the circle, okay? So a tangent line skims the edge. And if you really remember integrated 3, the line must be perpendicular or right angle to the radius at that contact point called the point of tangency, okay? So if you draw from the point of tangency to the center of the circle, the tangent line is perpendicular at a right angle to that radius. There's only one possible line that could do that at each point. If it's angled, it's not a tangent line, okay? Lots of real life applications for engineers and architects and et cetera, like I say all the time, all right? Millions of applications of calculus in the real world. Now, this one's kind of morbid, but it's real life. So the second deadliest stretch of road in America. By the way, no surprise, most of the deadliest roads are interstates, okay? There are some streets that qualify for this. There are some highways that qualify for this, but usually it's interstates. They're very fast, you have high speeds, they're very efficient to get us from point A to point B, but at those higher speeds, there's a lower survival rate, and that's where it costs you. So, Interstate 10 out in Arizona, very close to the California border. I've driven that hundreds of times. It is dangerous, all right? One person dies each year per 1.8 miles. Imagine that. In the next 1.8 miles, on average, somebody will die this year. And that 1.8 miles, and that 1.8 miles. That's scary, all right? But there's one place that's worse. I-26 in a state that is very close to Tennessee, the state of South Carolina. One of my best buddies, Jack, lives pretty close to I-26 in South Carolina, actually. And it is the single deadliest stretch of road in America. So, one person dies per, get this, 0.3 miles. Are you kidding me? That is very scary. So every 0.3 miles, I wonder how many feet that is. Well, I'm curious as a cat. It's probably one of my friends call me Whiskers. So what I did was, I did an old integrated 3 trick. I changed the word miles into 5,280 feet. Remember that old one? If you change that to 5280 and you do 0.3 times 5280 feet, you come up with 1,584 feet. Every 1,584 feet, somebody will die this year. That really brings it home how dangerous this is, okay? Very scary. Now, how does this relate to calculus? So if you're driving on one of these curvy sections of I-26, as you can see in the picture on your sheet there, if you're going this way and you lose control, let's say at this point, if you lose control and depart the curve, even on a curvy road out in the country, anywhere this could happen, your car travels on a tangent line once your tires lose grip with the pavement. So you travel on a tangent line, also true with hydroplaning, by the way. And when you take off the road, each point on a curve has a tangent line. Now, back in integrated 2 and 3, you learned that circles have tangent lines. It's not until calculus that you realize all curves, they don't have to be circles, all curves have tangent lines at each point, okay? So your car is going to follow this path. Now, the scarier part is like when a gigantic truck is coming this way and a truck driver loses control, they're going to go tangent, but that's going to take them into the oncoming lanes. When you go tangent over here, you go off and hit trees. Not good. When you go out of control this way, your tangent line takes you across the other lanes into oncoming traffic, even more dangerous, and then eventually off the road if you even make it that far. Okay? So, when these accidents happen, they're often related to tangent lines. Okay, so tangent lines are back in integrated class. What do they have to do with calculus? All right, find the line tangent to And I've written an equation for you to model this picture, this part of the interstate, okay? So I took the picture off Google Maps, and then I started doing math to try to interpret the curve, and I got this equation as a rough interpretation. So this is the interstate curve. We want to find the point 1, -1. So let's say this is like 1, -1. This is where the car broke free right here, off the road. That's its point of tangency, all right? Can you write the equation of that line? Now, remember the equation of a line? Isn't that like y = mx plus b? And there's actually another form that we'll use today. But in general, lines are y = mx plus b. Those are linear equations. Okay, so I want you to write an equation like that for me to explain what happened in this accident. What path did the car take here? Okay, so to write the equation of, don't even worry about tangent yet. Just think about the word line. Let's just go back to like integrated 1, okay? If you see the word line in math and you have to write the equation of a line, all you need are 3 things. Once again, calculus comes in 3s. All you need is an x, a y, and a slope. If you can get an x, y, m, you can write any equation of any line at any level of math. So first, what's the x? That's given, it's 1. So we're looking at x = 1. What's the y? That's given, it's -1. But I do want you to know where I got that from, because I won't always give it to you. So sometimes you have to find your own y. Did I just make that up randomly, -1? No. I made up 1 randomly, but then I took the 1 and what did I do? I plugged it in the original equation for x. So I replaced these 2 x's with 1, okay? What does the original equation give you? It says right there, y coordinates. The y coordinate shall equal 1 minus 2 times the current x coordinate over 3 times x coordinate minus 2. So I actually took 1, plugged it into the x's, came out with that y. You might have to do that for yourself sometimes. So it's pretty important to note right here. I do want to note this for future problems when they get a little harder. That number came from taking 1 and putting it in the original function. We'll call it f. Let's call it f of 1, okay? So the only thing you use the original function for, of course, in math is for the y coordinate. That's a fact. Now the slope, on the other hand, okay, back in the integrated classes, we give you 2 coordinates, and all you have to do is y2 minus y1 over x2 minus x1. It's rise over run, but not in calculus. You only have 1 coordinate. So what is the slope of this tangent line? Well, we've kind of been hinting at this in chapters 1 and 2. The slope of a curve, or the slope of its tangent line, is the derivative, okay? So the slope is f prime at the given 1. So I really want you to start understanding that the derivative is there to find the slope for you. All right, so original, y coordinate. Derivative, slope. Let's take the derivative. Oh, I see an x on top and an x on the bottom. Quotient rule. Know your rules from past tests. High is on top, and ho is the denominator. So over here somewhere, let's tell you what, we'll do it on the sideboard over here. This will be my entire aside. All right, y prime equals, so this is why it's very important that you're learning the foundations of calculus, because we're going to start applying those, all right? So bottom stays the same, HODI high. So bottom stays the same times derivative of the top, d high. What's the derivative of 1 minus 2x? That would be 0 minus 2, so -2. Okay, HODI high minus high is 1 minus 2x times d ho. And the derivative of 3x minus 2 is 3 minus 0. So 3 over the bottom squared, okay? All right, now your choice. On a past test, I had you simplify these. So you would distribute the -2, and you would distribute the 3, and you would also distribute the negative to the end result down here, okay, this binomial down here at the end. Since we're plugging in a coordinate today, aren't we trying to find f prime of 1 currently? Or y prime of 1, same thing. You can, if you want to, you can just go ahead and plug in 1 for all the x's and not even waste a step simplifying. Might be easier just to change all these x's into numbers right now and do it numerically. Not a bad idea. Okay, so if there's nothing to plug in, you're going to have to simplify this. If there's something to plug in, I just go ahead and plug it in and not even simplify. So when you plug in 1, 1 times 3 is 3, minus 2 is 1 times negative 2. It's a little easier without the x's in there, right? The minus comes down. Plug in 1 here, you'd get 1 minus 2 is negative 1 times 3. And on the bottom, you would get 1 times 3 is 3, minus 2 is 1 squared. Okay? Less intimidating now. So now 1 times negative 2 is negative 2. 3 times negative 1 is negative 3, but it's a minus 3, which is a plus 3. And 1 squared is 1. And you actually end up with 1 over 1. That's pretty easy. 1 over 1 is 1. Okay, back over here now. So the derivative at 1 ended up being 1. Now, of course, they're hardly ever the same number, so that was coincidence. All right, that's how you get a tangent slope. Okay, so at the coordinate 1, negative 1, we got a slope of 1. All you have to do now is just write the equation. You're done. All right, remember y minus y1 equals m times x minus x1. Remember that that's called point slope form, okay? This is called slope intercept form. So y minus y1, that was negative 1, y minus the actual y equals m times x minus the actual x, or what we call x1, okay? Minus minus makes a plus. I don't know why you'd keep that 1 times. You wouldn't need to. Just drop the parentheses and just call it x minus 1. That's it. If you want to subtract 1 from both sides, you can put it into y equals mx plus b form. So if you subtract 1 from both sides, it would be y equals x minus 2. I would take that as well. There's not necessarily an advantage. Either one of those is fine. Okay? So you can solve for y or not solve for y. But if you want to write this in your notes, if you need this, y minus y1 equals m times x minus x1. That's what we're using, the old point slope. And that's how easy it is to write the equation of a tangent line. And of course, every accident that involves a fatality or a serious injury, they have to do an accident recreation and try to figure out who is at fault and keep all the information for future court cases and everything else. So this is really important here, okay? Sad, but important. All right, now let's try letter B. So now we've got a cube root function. Remember, cube root from integrated 3 is the sideways snake. Remember that? Yeah, know your pictures for this class, that's for sure. Know your shapes. All right, so x equals 1. That must be where this is right here. So we'll just mark that if you want to mark it. This is just a visual. You won't need that in the future when you do this problem, but I want to show you something here. So remember we said if you have any curve and any single point, there is only one tangent line per point, okay? That's a big deal in calculus. So there's this tangent line that like skims the edge of that point right there, okay? That's a tangent line. Now I'm going to mix it up a little bit this time because sometimes they ask you for the normal line equation. All right, what in the world is a normal line, you're wondering? So a normal line is where you pick a point and you draw the line that is perpendicular to the tangent line, okay? So while the tangent line rests on the outside, the normal line actually pierces right to the center of this thing, all right? Not the center of the snake, but kind of the center of gravity and some stuff you'll do later, maybe at a Calc 3 level, all right? Just like the circle now, over here in the circle, when we had the tangent line, and I mentioned that perpendicular, this would be the normal line. It actually does go right through the center of the circle, okay? It will hit the actual center of the circle in circular equations. Now this one over here is a sideways snake, but it does pierce to down here, all right? The center of this mass over here. So that's what a normal line is. All right, guess what? Don't worry about the word normal yet. It's a line. All I need for a line is 3 things: x, y, m. I can write any line equation, okay? And then I just toss it into y minus y1 equals m times x minus x1 from there. That's it. Okay, so x is given 1. Ah, see, this time I didn't give you the y-coordinate, but you can find it yourself because you've got an equation right there. The y-coordinate is always f of whatever that is. But the slope, isn't that always f prime of whatever x is given, right? And that's the difference between y-coordinates and slopes. They're very different, actually. Okay, let's go find f of 1. Take 1, put it in the original function to get a y-coordinate. 2 times 1 is 2. 2 plus 6 is 8, so you get cube root of 8. Oh, thank you, Mr. Wade. We really appreciate that perfect cube in there. I hope you do. Cube root of 8 is 2. Nice. Know your perfect cubes. Okay, find f prime of 1. Oh, we need a derivative, don't we? All right. Let's go over here. Let's rewrite this as, since it's not derivative ready yet, isn't cube root just 1/3 power, as we've frequently mentioned? So you want to feel very comfortable with your basic derivatives by now, so that you can do these problems easily. So the derivative to find the tangent slope would be 1/3 to the front. Base always stays the same. Drop the power by 1, so 1/3 minus 3/3 basically is negative 2/3. Okay? Because that was minus 1 minus 3/3, right? Chain rule, don't ever forget that chain rule. You'll ruin the whole problem. Derivative of the original base that stayed the same, 2x becomes 2 plus 0. So your chain rule is 2. Okay? And I'd prefer not to leave that negative power. Let's make a one long fraction bar right here. Who's upstairs? 2 is over 1, so 2's upstairs. Times 1 is upstairs. That's the only thing upstairs is 2 times 1. So that's 2 upstairs. Who's downstairs? 3 is downstairs. This is hanging out on the side of the fraction, but side does mean top, so this is technically on top with the 1, but the negative power says, nope, you're going to go downstairs. And you end up with this to the positive 2/3. Okay, there's your derivative right there. I probably wouldn't even change it back into radical form. I think I would leave it because we talked about like 2/3 power back in integrated 3, and even if you had me in integrated 2, those fractional powers. So here's what I would do. Aren't we looking for f prime of 1? So shouldn't we take 1 and put it into x in the derivative? So we'll get 2 over 3 parentheses. Plugging in 1, 2 times 1 is 2, plus 6 is 8 to the 2/3. All right, 8 to the 2/3. Okay, let's get this out of the way for now. All right, now we have to go back to integrated 3. How to do fractional powers. You remember you always do the root first and do the power last. Remember this? Do the cube root of 8 because it's easier always to do the root first. You could do 8 squared is 64. I don't know why you would. Cube root of 8 is 2, then 2 squared is 4, okay? So 2 over 3 times 4. Fractional powers in review, right? Okay, this right here is a cross cancel because it's multiplication. So that's actually 1/2. So 1/2, let's put that over there. But then 2 times 3 is 6. Okay, 1/6. Let's just put that up here. So 1/6 is now your f prime of 1. So I gave you an x, you got the y, you got the slope. Those are your 3 ingredients. And now it's time for a twist. So pay attention. If it says tangent line, you're good. Just write the equation from this. But if it says normal line, that's the one that's perpendicular to the tangent line. So just one little twist that you have to pay attention to. The derivative only gives you the tangent slope. So 1/6 is the tangent slope. But I want the normal slope, which is perpendicular. Does anybody remember from those old classes that the fancy symbol for perpendicular is the upside down capital T? You don't have to, but if you really want to be clever, you can put that in there. The perpendicular slope, the normal line slope. Do you remember how to do perpendicular slopes in integrated 1, 2, and 3? If this is the tangent slope, don't you flip it upside down and change the sign? Remember those old perpendicular questions? Hey, they're on the ACT. You got to know these. So you take 1/6, which would have been great for your tangent slope. Let's cross that out. You flip 1/6 over and make it negative 6 over 1, or negative 6. That's your normal line slope. So you had to get the 1/6 first, like you have to figure that out. But then ignore it, flip it over and change it, and use this one instead, all right? This is your normal line. Now you're done. Now just write this. Y minus y1, which was 2, equals slope negative 6 times x minus x1, which was 1. You're finished. You don't even have to distribute the negative 6 and then add the 2 over. You can, you don't have to. You're done, okay? So watch out for the normal line. Take the derivative, get the tangent, flip, change sign, boom, roasted. All right? Challenge us. Okay, let's try letter C. Now I've given you the equation. The tangent line equation is y equals negative x plus 3. Looks just like a y equals mx plus b, right? That line is tangent to, oh, that's a parabola. X squared plus 7x plus unknown constant, some number, okay? Find the constant c, all right? So you've got a parabola, clearly. You've got a tangent line that is negatively sloped, so it's probably like this. Oh no, Mr. Wade, you missed the parabola. Okay, you've got to figure out the c. Isn't the number being added at the end, remember the transformations back in integrated 2 and 3? Isn't the number at the end the up and down shift, the vertical shift? You remember this? So you have to pick the c that vertically shifts the parabola until it docks on top of that tangent line right there, okay? If you shift it just enough, there should be one place where you can force it to be tangent. All right, so that's the visual, but now how do you pull that off, right? Okay, what's the first thing we do when we see a tangent line equation? Don't we find our x, y, m? So let's think about that, okay? All right, I gave you an xy in the first example. I gave you just x in the second example. You got the y. Now I didn't give you either one. We don't know where this thing is actually docking in the space station here, right? This is some kind of spacecraft that's trying to link into another one up in space. We don't know either one of those, the x or the y. So the point of tangency is completely unknown. But there is one thing you do know. The slope is sitting right there in plain sight. If that's y equals mx plus b from those old math classes, integrated 1, 2, and 3, doesn't b mean that the y-intercept is 3, the line's crossing the y-axis at 3, but more importantly right now, isn't the m or slope of the tangent line negative 1? It's the coefficient of x only if y is by itself. If y is by itself, you can see the slope. The slope is negative 1. That's a start. That's a start, even though we don't know these two. Now we'll need to find these two. But hey, the slope is negative 1. Now wait a minute. Okay, that's really from middle school, that you can see the slope sitting in front of the x. But now from calculus, how do we get the tangent slope? Isn't the tangent slope from the derivative of the curve? Not the derivative of the line, but the derivative of the curve. This is the curve it's tangent to, the parabola. So that negative 1, what I did was I actually worked it out with actual numbers, and then I took away the numbers and hid them from you. But when I worked it out, how did I get negative 1 for the tangent slope? Wouldn't I have just done the derivative of the parabola, right? Okay, let's take the derivative of the curve. Y prime of the parabola would be 2x plus 7, and the derivative of plus c, or any constant, is 0. Okay, don't treat c like a variable, it's a number, it's constant. So the derivative of the parabola is 2x plus 7. Isn't the derivative the formula for finding all the steepnesses all the way through the parabola, right? These are all the tangent line slopes. So the derivative of the parabola is the slope of the parabola at any x. But wait a minute, we know the slope is negative 1. We don't know the x for the first time ever, but we know that the slope should have an outcome of negative 1. Aha! Derivative must equal tangent slope, okay? And you can just ignore the y prime now. Go solve this 7th grade equation, maybe even 6th grade equation. That's it. So the derivative of the curve shall equal the slope of the tangent line, as we said before. This one, we're just kind of going backwards. Subtract 7 from both sides. That would give you 2x equals negative 8. We're there now. Divide both sides by 2, x equals negative 4. And that's actually what I used when I did the calculation. I just didn't tell you that. You found it on your own. So x is negative 4. Okay? All right, let's reset. We'll make like a brand new xym here. We now know the x is negative 4 right over here. Let's put negative 4 right there in our picture. We know that, oh, still don't know the y. We know the slope is negative 1. Okay, now I've got to tell you about something really important that we haven't talked about yet, and this is a big deal in calculus, okay? You'll do it often. How do we get the missing y coordinate? Because I need the y coordinate, okay? Well, don't you take negative 4 and plug it into the parabola and you could find out the y coordinate? Okay, great. Problem. If you plug negative 4 in for the x values of the parabola, you'll still have unknown c and you'll have unknown y. That's 2 unknowns. You can't solve an equation with 2 unknowns. That's not good. Here's the big breakthrough that's such a big deal in calculus. Is that point lying on the parabola? Yes. Isn't the point also lying on the line, whose full equation we do have with no c's in there, right? The tangent point, the point of tangency, will always be not just on the curve, but also lying on the line at the same time. So I could take negative 4, and even though I'm supposed to put it into the curve, I could sneak it into the tangent line and get the same outcome. Big breakthrough, okay? Because they're sharing the same point. So negative 4, plug it into negative x plus 3. Negative 4 makes positive 4, plus 3 is 7, y equals 7, boom, breakthrough. That was actually negative 4 comma 7 the whole time, and all the information's on the board. You just have to see it, okay? Now, normally, you would take the x, the y, the m that we just got, and you would write that tangent line like we did before. Oh yeah, I already wrote it for you. That's how I got it myself, okay? I've already done that for you. What we're trying to find is c, but now you have enough information. If you plug in negative 4 for the x's, and then simultaneously 7 for the y's, isn't negative 4, 7 a point that's on the parabola, the only point that we know? So if negative 4 goes there, and 7 goes there, the only unknown left will be c, and that's how you find it. So it's a little higher level problem, but very similar, okay? Similar theme. So let's try it. 7 for y, we get 7 equals x squared, so negative 4 squared, plus 7 times x, which is negative 4, plus c. Negative 4 squared is positive 16. That's a minus 28, and that's a plus c. And 16, the difference between 16 and 28 is 12, but the 28 is stronger, so it's negative 12. That's how I think about it in my head, and probably most of you do as well. Add 12 over to the other side, c equals 19. Okay, so it's a 19 shift on this parabola, and if you shift by 19, it will land right on top of that tangent line. How about them apples? Letter D, challenges, Mr. Wade. All right, twist my arm. Okay, it's our first abstract problem of the year. H of 2 equals 2, h prime of 2 equals 4, and things get really abstract here. So those are clues, those are hints. We're going to find the tangent line to g of x. What's g of x? It's x squared distributed to some other mystery h of x function. We don't even know what h of x is. We don't know what g of x is clearly, but we do know that h of x, if it got upgraded by x squared to every single term, would become g of x. That's all we know. So 2 equations you can't even really picture or wrap your head around, and yet there's just enough information here where we can still do the problem. Okay, so first of all, line. 3 things, x, y, m. That's all I need to write any lines equation since middle school. So x given 2. That goes there. Y. Isn't y what happens when you plug x into the original function? Now let's see, is this the tangent line to g or the tangent line to h? It's the tangent line to g. So the y-coordinate would be whatever g of 2 is, but the tangent slope would be whatever g prime of 2 is. And that's one of the major themes here. So I want you to know that your entire life when you've been doing mathematics, you've been plugging numbers into functions and getting only y-coordinates. And all of a sudden in calculus, you're also plugging them into the derivative and getting how steep the curve is, how steep the tangent line is. All right, g of 2. I don't really have a full equation for g, but I kind of do. G of x is x squared times h of x. So g of 2 would be 2 squared times h of 2. We could do that. 2 squared is 4. Now we don't have an h equation, but we have a clue because I would have to give you a clue. H of 2 equals 2. Whatever the h of x function is, I know what it is, but you don't. But when I plugged in 2, I came out with 2. So h of 2 becomes 2. 4 times 2 is 8. So you've got just enough clues. And they like to give you these abstract problems sometimes. A lot, actually, on the AP test. Okay, let's go find g prime of 2. Now, what do you need before you find g prime of 2? You need g prime of x in general, right? We need to find g prime of x. We'll do a little aside down here. Okay, let's go find g prime of x. And that would be the derivative of x squared times h of x. Is that a variable times a variable? Is that x squared times h of x? Variable times variable, you must do the product rule unless there's some way out of it to simplify. Yeah, you can't simplify x squared times h of x. So we do a product rule. Ho-de high, second one stays the same, h of x, times the derivative of the first, which is 2x to the first, plus high d ho. First one stays the same, x squared, times the derivative of the second, h prime of x. There is your product rule. Now let's go find g prime of 2. All x's become 2. So that would be h of 2 times 2 times 2 is 4, plus 2 squared is also 4, times h prime of 2. And you don't know what the h function is. Only I do behind the scenes. But I've given you h of 2, and I've given you h prime of 2. So if you just follow the rules of mathematics that we've already laid out in this course, you can even do the weird abstract problems like this, all right? So h of 2 will be replaced by 2. Let's put a 2 right there. 2 times 4 is 8. Plus, carries over to there. 4 times h prime of 2 can be replaced by 4. And 4 times 4 is 16. And 8 plus 16 is 24. And now you have x, y, m without even knowing what g of x or h of x truly is in real life. All right? Because you don't need it. Okay, in conclusion, final answer. Y minus y1, let's see, that's 8, equals m, 24, times x minus x1, which is 2. And that's the equation of a line. There you go. All right, let's do the last one over here. Lowercase Roman numeral 2. Slope of y equals g of h of 2x. It's a double of. This is what we studied in integrated 3 and even integrated 2, called a composite function. When you take one function and you stuff it into the x's of another function. Hopefully you remember this in your past. Composite function. For the first time this year, we are going to take the derivative of a composite function. All right? So when one's stuffed inside the other one. Well, slope means derivative, of course. So y prime equals, how do you take the derivative of a composite function? It's very similar to what we've done before. It's not a lot of difference here, but there is a trick to it. The derivative of g, always start on the outside, right? The derivative of g is clearly g prime. That's all we can put. But doesn't the base stay the same? And h of 2x is the base. Okay, guess that'll do it. Wait a minute. Hold on a second. Doesn't every derivative get times the chain rule? Go back to the original base. Let's even do an aside for this one. On the original base, the base was what? H of 2x. Okay, that's your original base. The derivative of the base, the chain rule of h of 2x. What's the derivative of h of 2x? Derivative of h is h prime, but its base stays 2x, but then you go back and say, wait a minute, 2x, you never went through the derivative process. The chain rule of 2x is 2. The derivative of 2x is 2, right? So the chain rule is all this with an extra little chain at the end. It's one of those double chain problems that can be so tricky until you get really used to them, and then you'll never miss them again once you get used to them. Okay? So there was a base of h of 2x and then a little base of 2x. So if there's like a medium base and a small base, you're going to get a double chain. All right? There is your derivative right there. Okay, what's the last thing you have to do? Take 1, plug it in for x. So y prime of 1, let's call it, all right, equals g prime of h of 2 times 1 is 2. H prime of 2 times 1 is 2 times 2. What is h of 2? Oh, wait, we had hints in the previous problem. This is still part of the same problem. H of 2 was 2. So I'll put a 2 right there. Now we're going to find g prime of 2 in return. So g prime of 2, well, I didn't give that to you, but you found it when you did your XYM. It's still lingering over here. G prime of 2, we just found out in the last problem, was 24. So this, g prime of 2, is 24. And then that's times right there, of course, times h prime of 2, that was given on the other board. H prime of 2 is 4. Times 2, all right? And a couple of tips for doing this without a calculator, because this is a non-calculator class for the most part. I would probably multiply the small numbers first. I think 4 times 2 is 8, probably better, and then wait till the end to do 8 times 24. Okay, now when you multiply 8 times any number, you can do double, double, double. So if you want, if that makes sense in your brain, you can do double 24 is 48, double 48 is 96, double 96 is 192. If you can do that, great. If you can't, distribute the 8. Remember, it's 8 20s plus 8 4s is actually the way you should be thinking about that. So 8 20s makes 16 followed by a 0, 160. And then, of course, 8 times 4 is on the times tables. That's 32. Now, if you can do that in your head without writing it out, you will be a super duper calculus student, okay? So, you know, when I look at 8 times 24, in my head, I just think, oh, 160 plus 32, 192. And actually, I end up doing it so often, I can just remember it's 192, but with some numbers, I can't. There are plenty of numbers that I don't know what they are when you multiply them. But I figured out back in the 5th grade that I could do these little mental tricks and just go, oh, 8 20s and 8 4s, shouldn't we just be doing that? Isn't that easier? Shouldn't the teacher be teaching us this? So I teach you all my secrets so that you can be just as good, actually probably better than me when it comes to math, all right? So that's how you do it. All right, and that's it. So now, what is that, 3-1? So you got homework, so go give it a try. And also watch 3-2.